Good afternoon and welcome to another Research in Action brought to you by the Division of Research at Florida Atlantic University. We're very happy you're here and we hope that you're staying safe in these uncertain times. Before we get started, I would like to go through a few logistical items. Because of the number of attendees, we do not allow for you to ask your questions verbally, but we definitely want to hear your questions and address them. So if you hover your mouse at the bottom of your screen, you will see a question and answer button, a Q&A button there. If you push this button, a pop-up will come up and you can type your question there. You can do this anytime during the presentation. We will start addressing the questions at the end of after the presentation. If we do not get to your question during our allotted time, we will ask our presenter to answer the questions offline, and will then post the answers together with a recording of this presentation on our website, the Research in Action website at FAU. With that, it is my great pleasure to introduce today's speaker, Dr. Ata Sarajedini. Dr. Sarajedini is currently the Bjorn Lamborn Endowed Chair in Astrophysics at FAU. He also served as Dean of the College of Science here at FAU, and before that came from UF. Dr. Sarajedini's research focuses on resolved stellar populations in local group galaxies, which includes field stars, open and globular clusters in the Milky Way, and numerous nearby dwarf galaxies. And what that all means, he's going to hopefully tell you in the next few minutes. With that, welcome, Dr. Sarajedini.
Thank you very much for having me today. It's a pleasure to be able to speak to this group about the Hubble Space Telescope and the most important images taken by HST. Let me go ahead and share my screen. All right, great. So I'll be speaking today about the most important photos ever taken by the Hubble Space Telescope, or an alternative title is How Do Galaxies Form? And I want you to keep that in the back of your mind as we go through the presentation. What we're trying to do in the end is try to understand how galaxies form. And we're going to do that using images from the Hubble Space Telescope. Now, before we actually start into the meat of the topic, what I really want to do is talk about science and how science works and what science is. So what is science? Well, it's a tool to better understand the natural world. We will never fully understand the natural world, and so science is going to help us to better understand it. And how does a typical scientific investigation progress? Well, after you ask a question, then you go out and you gather observations or data to help you answer that question. Observations typically require an explanation. Another word for explanation is model, hypothesis, or theory. Once an explanation is devised, and every good explanation has a prediction, and then we take the prediction and we go back to the observations and we look and see if that prediction comes true. If it does, then our explanation is probably correct. If it doesn't, then we have to go back, modify the explanation, and hopefully make a better prediction that is more in line with the observations or the data. That's how science progresses. It's a self-correcting process. The self-correction could take anywhere from a few months to years to the decades, but that's how science progresses. It corrects itself, but that self-correction can take a certain amount of time. Okay, so that's the basic idea of how science works. And what we're going to try to do is to use the observations of the Hubble Deep Field in these images I'm going to talk about to explain or devise a theory for how galaxies form. And then we're going to make a prediction and come back and hopefully close the loop on if our prediction, if our model or explanation is correct. Now I want to talk about the concept of the universe as a time machine. This is very important in astronomy because the speed of light is finite. 186,000 miles per second, or 300,000 kilometers per second. So light takes a finite amount of time to travel through the universe. So for example, the moon is 1.5 light seconds away. The sun is 8 1/3 light minutes away. In 1 light year, the distance light travels in a year is 6 trillion miles. When you look out into space, you're looking back in time. We're seeing the sun as it was 8 minutes ago. We're seeing the nearest star as it was 4 years ago. We're seeing the nearest large galaxy, the Andromeda Galaxy, as it was over 2 million years ago. Now, it sounds like the universe being a time machine is actually a disadvantage. In reality, it's an advantage. You can look out into space and look back in time, back into the history of the universe, and use your observations of distance as a way to understand how the universe evolved over time. So what is so special about the Hubble Space Telescope? Well, there are two things. One is it's above the Earth's atmosphere. So there is no blurring of the images that we're going to be observing by the atmosphere. There is no blurring at all. It's completely and utterly clear. And I'll show you some examples of that in the next slide. The other advantage is that the Hubble Space Telescope, HST for short, is exceptionally good at pointing and tracking objects in the sky. And so what I say here is that it can shine a laser beam on a dime 200 miles away and keep it on that object over time. So not only is there no blurring by the atmosphere, but it's exceptionally good at tracking and pointing at particular objects in the sky. And what this picture here shows is the optical telescope assembly, where the light comes in from the left. That's where the opening is, comes in through the tube, and then the object here is the primary mirror, where it says a 2.4 meter primary mirror. That's a mirror that bounces the light back up to the left, and then inside the secondary mirror, the light bounces off of that mirror and then back down to the back, where the scientific instruments are all in this box in the back of the telescope. And the beauty of it is that the box is modular, and so instruments are back there and they can be changed out, modified, improved, whatever over time. And in the era when the space shuttle was flying, that was used to go up to the telescope and put new instruments in and do maintenance on it, put in new gyros, all the things that could wear out could then be replaced. And every time there was a servicing mission by the shuttle, you basically had a new telescope. And so that was another kind of advantage, another power of the telescope itself and the way it was designed. But the point is, it's above the atmosphere, there's no image blurring by the atmosphere, and it's very good at pointing and tracking objects in the sky. So here's some examples. At the top, on the left, is a picture of a galaxy from the ground. You can see it's a galaxy, naturally. It's got spiral arms, it's got a central region that's fairly bright, but it's kind of fuzzy. On the right is the same galaxy with Hubble Space Telescope. And you can see just exactly how much more detail is visible in that galaxy. You can see the spiral arms much clearer. You can see individual stars. And then, of course, look at the other galaxies that are around it. This piece of fuzz in the lower left that resolves into a nice galaxy. You could do studies of that as well. So it's obvious that going above the atmosphere, eliminating the fuzz of the atmosphere really provides much better resolution for what you're trying to observe. In the bottom is an image of what's called a globular cluster. The difference is not so dramatic here, but on the left is the ground-based image. On the right is the Hubble Space Telescope image. And suffice it to say that in the HST image, we can go right to the middle and actually measure the brightnesses and colors of these stars right in the very center, whereas the ground-based image is much too crowded and unresolved to be able to do any work right in the middle. So HST, this is just an example of how much improved the resolution is by going above the atmosphere and eliminating all this atmospheric blurring that is afflicting ground-based telescopes. This is a slide that was actually made in 5 years ago, 2015, for the 25th anniversary of the Hubble Space Telescope. HST was launched in 1990, so actually this year, 2020, is the 30th anniversary of the telescope. But this is just some facts and figures about the 25th anniversary. And obviously it's much beyond that, but it gives you a sense of just how accomplished the telescope is. So, for example, it's generated over 10 terabytes of new data per year. It's got over 1 million observations. It's traveled more than 3 billion miles. I mean, it's really outlasted its original expected lifetime by quite a bit. And of course, like I said, this is 5 years ago. So now it's even well beyond these milestones in terms of producing scientific data. And every single observation HST has ever taken is available on the web to anyone who wants to look at it and access it. It is, after all, a taxpayer-funded facility, and so everyone's taxes is paid for it, and so everyone has equal access to the data that the telescope has taken. And obviously, you need to have the knowledge to analyze the data and access it and download it and all that, but all that information, most of it anyway, is available on the website, and everyone's welcome to get on there and explore the archive of observations and see what's available there. All right, now let's get on with the actual topic at hand, which are these deep fields that HST has focused on very close to the time since it was launched. So the first one is called the Hubble Deep Field, and this image here shows you the location of HDF, the Hubble Deep Field. Many of you know what the Big Dipper is. There it is. That dot, right, the red dot, is the location of the Hubble Deep Field, and there's the North Star. It was chosen specifically to be an apparently blank patch of the sky. We didn't want any bright stars in the field because we're going to observe this particular field for many, many, many orbits and many days. And in this one in particular is 342 separate exposures over 10 consecutive days in 1995. And this animation just shows you, there's the Big Dipper, just shows you where the location of HDF, the Hubble Deep Field, is. So the important thing here is it was chosen to be devoid of bright stars. And the idea was there's no bright stars there, so what actually is there? And we're going to take a very large number of HST images, combine them together, and figure out what is there. And this is what came out. This is the first Hubble Deep Field released in 1996, and it was taken with what was called the Wide Field Planetary Camera 2, WFPIC 2 for short. And you can see primarily in this picture, there's all kinds of galaxies. There's over 3,000 galaxies in this one picture. Everything in this picture that has these spikes, what are called diffraction spikes, is a star, but everything else is a distant galaxy. So if you look at it quickly, you can see there's a star here, there's one over here, there's a few other stars scattered about, but there's one over here, but the vast majority of these objects, these fuzzy objects, are distant galaxies. So think of each of those galaxies as akin to our own Milky Way galaxy, which contains 100 billion stars. So there's at least 3,000 such galaxies here. You also notice that the galaxies in this field have different colors. We're going to come back to that later about what that actually means. But you'll notice that there's a lot of galaxies, they're all different colors, and they're distributed fairly randomly, in this field. All right, so a few years later, they decided to do another field called the Hubble Ultra Deep Field. And this time, they're using a different instrument, what's called the Advanced Camera for Surveys. And instead of being in the northern hemisphere, this one is going to be in the southern hemisphere. And this graphic here just shows you the location of the Hubble Ultra Deep Field. And using the Advanced Camera for Surveys, this is now hundreds of separate exposures taken over 4 months in 2003. And these are all combined together in various ways to produce the resultant deep field image, which is going to be much deeper, you'll see much fainter objects in it than you would in just one picture by itself. So here's the ultra deep field. So this is the Advanced Camera for Surveys, and you notice a similar kind of behavior. These are mostly galaxies, 10,000 some galaxies in this picture. The objects with diffraction spikes, of which there are very few, but there's one here, there's one there, there's one up here. Those are the stars, but there's very few of those. Most of these almost all of these fuzzy objects are distant galaxies. And once again, you notice a variety of colors in these objects, some of these galaxies. Some are yellow, some are orange, some are red, white, all different colors. You also notice that if you compare this image with this one, you'd be hard pressed to tell the difference. That is to say, the distribution of galaxies, just by just using your eye, is to first order about the same. This and this. There is no apparent difference in the distribution of galaxies, even though one of the, the first one was in the northern hemisphere, and this one is in the southern hemisphere. So whether you look in the north or in the south, you're going to see the same universe. That's the conclusion of the similarity of these two images. And what that underscores is what we call the cosmological principle. The cosmological principle says that the universe is homogeneous and isotropic. Homogeneous just means that it's uniform throughout. Isotropic means that no matter what direction you look in the sky, you're going to get the same answer with respect to the properties of the universe. And the similarity of this image and this one underscores the veracity of the cosmological principle. So that was actually reassuring to see that the cosmological principle was borne out in these observations. Now, what they did then was they went back to the ultra deep field and they extracted a portion of the ultra deep field that had many more observations than the rest, and they put those together. And so this represents 2 million seconds, 23 days of exposure time, a subset of the ultra deep field. This is now called the extreme deep field. And so there's what that looks like. It's very small. You can see compared to the full moon, it's a very small part of the sky, but the conclusion is largely unchanged. We're able to see fainter, we're able to see deeper, fainter galaxies, but the conclusion is largely unchanged, that we're seeing galaxies with a range of colors and that are fairly uniformly distributed in this field. Now, one of the things you'll notice, as I said earlier, is the galaxies have different colors. And in particular, this slide shows that there's about 28 or so that are very red in their colors. And they're just numbered here, but you can also see them over here. So for example, this number 1, Galaxy 1, is over here at the upper left in this mosaic array. And so the question is, why are these galaxies so red? They're extremely red. And the question is why? So I want to take a little tangent and talk about why these galaxies have the colors that they do and why these particular ones are so especially red. And it has to do with what's called the Doppler effect. The Doppler effect has to do with the idea that when an object is moving, in this case this train, and it's giving off sound, which is a wave, that the direction that the object is moving, if it's moving to the right, then the sound waves are going to be compressed to smaller wavelengths on the right and longer wavelengths on the left. And so the person over here on the right is going to hear a higher pitch than the one on the left, who will hear a lower pitch, because these waves are compressed on the right and expanded or extended on the left. So this is what happens with sound. But the exact same thing happens with light. Light is a wave. It behaves like a wave. And so when an object is moving toward us at reasonably high speed, then the light waves it's emitting are going to have shorter wavelength. That means they'll appear bluer. And if it's moving away from us, the light waves it's emitting are going to have longer wavelengths. That means they'll be redder. So objects that are moving away from us will appear red. Now, this is what happens with light, and it's called redshift. And it was actually observed in the early 1900s by Vesto Slipher. And what this shows here is, in the middle are images, pictures of these galaxies in these different clusters of galaxies. And on the left are the spectra of those galaxies. The light from those galaxies is dispersed into its component colors. And then this line here, which is one of the lines that appears in the spectrum, is measured in terms of what wavelength it should have and what wavelength it does have. And it turns out that all these galaxies, their lines are shifted to longer wavelengths. And so that difference between where the wavelength the line should have and the wavelength that it's observed at is called the redshift. And that's, in this nomenclature, it's shown as delta lambda, which represents the difference in wavelength. So we define this number called redshift, which is Z, and it's defined to be the shift in wavelength, delta lambda, divided by the rest wavelength, or where that line should be in the absence of any motion. So Z, this redshift, is a measure of how fast this object, or each of these galaxies, is moving away from us. And we can convert that to kilometers per second, but most of the time we just work in redshift space, this number Z. And it can, and I'll show you in a second, but it can range from very small numbers, 0.1 to 0.5, all the way up to 4 or 5. That's the range that this redshift value can have. Then Hubble came along in the early in the 20s and basically realized that the recession velocity, the redshift of these galaxies, actually depends, or at least has a correlation with their distance. So he concluded that the further away a galaxy is from us, so the further along it is on this x-axis, the faster it's moving away from us, the higher its redshift on the y-axis. And so the distance, as I said before, is the time. How far away it is really how far back in time we're seeing it. And the recession velocity is the redshift. So what this says is that the further away you look, the further back you look in time, the faster galaxies are moving away from us. And this is what's called Hubble's law. And it's fairly straightforward. The recession velocity, V, is equal to what's called the Hubble constant times the distance. And like I said, it's a very simple, straightforward relation. And all it says is that galaxies that are further away from us are moving away from us faster. And this is Hubble's law. Every galaxy is moving away from us on the largest scales. The universe is expanding. And if you can measure the value of Z, which is the recession velocity, then you can calculate the distance using this relationship, using Hubble's law. Or vice versa, if you somehow know the distance, then you can calculate Z using this relationship. More often than not, though, this relation is used to measure the distance of the object, knowing what the recession velocity or redshift is. We measure the redshift from the spectrum of the galaxy, and we use this equation to calculate the distance. And then from the distance, we know how far back in time we're looking. So this is Hubble's law of universal expansion. And that explains why these galaxies are red. These are all red because they are moving away from us at very high recession velocities, very high redshift, and therefore they're very far away. The red galaxies in this picture are the furthest galaxies we can see in this particular field. And one way to show that is this slide. Excuse me. We can decompose the deep fields into these slices. We can slice the galaxies up into those that are 5 billion years into the past, 5 to 9 billion years into the past, and more than 9 billion years into the past. And that's what these planes show. The galaxies in this plane are fairly nearby, fairly close to us, fairly recent in their appearance. The ones in the middle are kind of intermediate, in their location and their time in the past. And then the ones on the right, those are the most distant and earliest and youngest galaxies we can see in this case, the extreme deep field. But the beauty of it is that once you measure the redshift, which is the recession velocity in this plot, you can go to this diagram and figure out how long ago you're looking at that galaxy in the past. So we can then make a plot like this. We can look at these images from HSD. This is a graphic produced based on some of the early wide field planetary camera 2 observations. called snapshots in time. So on the left, you can see elliptical and spiral galaxies as they are today. The universe is 13.8 billion years old. So 14 billion years old, that's today. And we can look back in time, 9 billion years after the beginning, 5 billion and 2 billion after the beginning, after the Big Bang. And what you see is galaxies look fundamentally different as you go back in time, as you go closer to where the universe was forming. And what you notice is, and again, this is just by eye, you notice that galaxies are less organized. They're more lumpy, let's say. They're not as well organized. They're not as beautiful, if you will, not as well put together earlier in the history of the universe as they are today. They're sort of more raggedy, and they have more lumps to them. There's more smaller portions to these galaxies. And so what this indicates is large galaxies like spirals, like this one, actually are produced, are assembled through a process of putting together much smaller galaxies in a fragmentation and accretion process, where small galaxies come together, they combine, they assemble and organize themselves over time into larger galaxies that look more organized and more symmetric, let's say, today compared to, say, a few billion years after the Big Bang. Now, this was assembled by some scientists at Space Telescope Science Institute, but we can look at this as well in one of the deep fields. Here is the ultra deep field. I just extracted a small portion of it within this square to kind of zoom in and show you what these galaxies look like in the past. And you can see that these galaxies, they appear to be spirals in some sense, but they also have little knots in them, and they're surrounded by smaller dwarf galaxies that would in the future collide and combine and accrete to form larger galaxies like the Milky Way and the Andromeda Galaxy, if you're familiar with that. Here's one right here that I'm just pointing to. This is a galaxy that's much more grand design, if you will, compared to the galaxies at higher redshift. And so what that shows is that this one is probably closer to us and is being observed more recently and later in its evolution. And here's just an example. This is the Andromeda Galaxy. Many of you are familiar with it. It's also called M31 in the parlance of professional astronomers. This galaxy is about 2.2 million light years away. It's a spiral, very similar to ours. And it has two dwarf galaxies. This is M32 over here, and this is NGC 205. These are dwarf galaxies that are left over from the process that formed the larger body of the Andromeda Galaxy. So think about forming this very large galaxy through the process of hundreds of these tinier, smaller dwarf galaxies colliding with each other, sticking together and combining to form this very large, more massive Andromeda Galaxy. That's the paradigm that we're looking at when we look at galaxies in the deep fields, and we know their redshifts, so therefore we know their distances, so we know how far back in time we're looking in the history of the universe. And we see galaxies in different stages of formation at different redshifts in the deep fields. And similarly, this is the Milky Way. So if you go out at night on a very dark site, this happens to be a wide field photograph of the Milky Way, but if you're at a dark site, you'll see this band of light that, I'm having a hard time getting my cursor here, but this band of light that extends from horizon to horizon. And if you're in the southern hemisphere, you also see these two fuzzy objects here. These two objects are what are called the Magellanic Clouds. There's the large one and the small one. And they are similar to those dwarf galaxies around Andromeda. These dwarfs are orbiting our galaxy, the Milky Way, and represent what's left over from the process that formed the larger portion of our own galaxy. And so if you look at other galaxies like ours, or other spiral galaxies around, in our local area, you'll find many of these dwarf galaxies orbiting the larger spiral galaxies as remnants of the process that came together to form these larger, more massive galaxies like the Milky Way and Andromeda. And this is just an up-close picture of the Magellanic Clouds. This one here on the right, that's the large one. The one on the left is the small one. Our Milky Way galaxy has a mass of about 100 billion stars. Each of these galaxies is probably 100 million or so to a billion or so stars each, and they're orbiting ours. And if you study these galaxies in detail, what you find is there's actually stars that go between the two, that there's a bridge, a filament, if you will, of stars that go between these two, showing you the remnant of the gravitational interaction that happened in the past that was integral to the formation of our own galaxy through the process of destruction and accretion of smaller galaxies like these two. Now this is another picture of our own galaxy. So the fuzzy thing in the middle, that's the plane of our own Milky Way. And all these other dots, these dots are other dwarf galaxies that are orbiting ours. So the Magellanic Clouds, the one I just showed you, are these two fuzzy pieces here. And the other red dots are another couple dozen other dwarf galaxies that are orbiting ours and that are thought to be the leftovers of the process that formed the Milky Way itself. This process took place soon after the formation of the universe. Maybe 1 billion years or 2 billion years after the Big Bang, this process was pretty much done. And that process left over these dwarf galaxies that are shown by these dots and produced the Milky Way itself. Now, it should be clear that since we're inside the Milky Way galaxy, we can't fly outside it and take a picture of it because it's just much too big. So we have to be content with, this kind of a rendition for what our own galaxy looks like. But given that caveat, these are the locations of all the dwarf galaxies that are left over from the process that formed our own galaxy. And just to reiterate, our Milky Way would look very similar to Andromeda if you were to be able to observe it from outside. So the Andromeda Galaxy is very much a twin in many ways of our own in terms of appearance. Okay, so this is the graphic. So on the left is us. That's today. There's Hubble Space Telescope observing the universe. And so as you look out to the right, as I said, you look out into space. You're looking back in time. And so on the horizontal axis down here, we have the age of the universe as we look back. So the Hubble Deep Field looked back to about 1 billion years after the Big Bang. The Ultra Deep Field looked back to about 0.4 to about 0.7 of a billion years after the Big Bang. And we haven't even gotten to the first galaxies yet. So the Ultra Deep Field is just at the edge of seeing the first galaxies, the first stars, and we have a long way to go if we're going to see anything beyond the first galaxies and the first stars. And the idea here is that because we're looking out into space, we're looking far away, we're looking back in time, we're looking at fainter and fainter objects. Well, to look at fainter and fainter objects, you need either a bigger telescope. HST is only 2.4 meters across in its primary mirror, or you need to just observe a particular patch of sky for much longer than we have already. That's hard to do. So we're taking the other approach, which is to design and build and launch a space telescope that's much bigger than the Hubble Space Telescope. So as I said, HST has a mirror at 2.4 meters across. The next generation space telescope is called the James Webb Space Telescope, and it's going to have a mirror that's 6.5 meters across. And it's going to be hopefully launched next year, 2021, and it's going to be primarily designed to find those first galaxies and possibly even those first stars. It's going to be primarily designed to push this limit of the ultra deep field as far back, as far toward the Big Bang, as far toward the origin of the universe as we possibly can. And that's one of the goals of the James Webb Space Telescope is to see the first galaxies forming. But you can imagine that it's a challenging problem. So here's just a graphic showing you that. So what we have here is the different observatories on the left, from the ground-based observatories to the deep field, ultra deep field, and then James Webb. And then on the bottom, we have the redshift, the time after the Big Bang. So 6 billion years, 1.5, 800 million, 480 million, et cetera. So and that's the future. So the Hubble ultra deep field was able to take us to about 400 million years or so, maybe 500 or so after the Big Bang. But James Webb is really going to take us even further, and hopefully, as I said with the previous slide, back to seeing the first galaxies forming. At the moment, that is the holy grail of galaxy formation, is being able to see the first galaxies that formed in the universe. And this is another graphic that shows you the history of the universe in one shot. This goes the other way, unfortunately. This one shows the present on the right, excuse me, present on the right. And then as you go to the left, you're going back in time. And the first stars are here at 400 million years. And then you have the dark ages, and then you have what's called the microwave background radiation, which I'll talk about in a second. But that's that colorful region on the extreme left of this slide. And what we want to see, as I said, is the first galaxies before where we're at today, before the Hubble ultra deep field that we're able to observe today. And so here is what we have, the remnant of the Big Bang. This is a picture showing you what's called the primordial background radiation. These colors represent temperatures in all different parts of the sky. And the different colors are very, very small changes in the temperature of the sky in these various regions of the sky. Very small, as in fractions of a degree is what we're looking at here. And what you see here is variations of temperature and also variations of density, which represent what the universe looked like just before the first stars were able to form. It's what's left over from the Big Bang itself after 13.8 billion years of expansion and cooling off of the universe itself. And if we're going to find the first galaxies on the first stars, they're going to have to, their distribution in the sky are going to have to be consistent with what we see here as what's left over from the Big Bang in terms of when the first galaxies and the first stars formed, in terms of the distribution of temperature and density of material in the universe. Now, this was discovered, the primordial background was discovered by accident, actually, by these two gentlemen, Arno Penzias and Robert Wilson, in 1964. And they're actually standing in front of this horn antenna that they used to discover the primordial background radiation. It's called primordial because it's from the early universe. Background because it's everywhere, all over the sky. No matter what direction you look, you see this radiation. And that's what this slide shows. And radiation in that it's a form of light. It's a form of light. And the interesting thing about it is you can study the detailed properties of this light in all different parts of the sky. And it is amazingly consistent with the theory that we've devised for the Big Bang and how the Big Bang happened and how the Big Bang progressed. Okay, so here are my takeaway points from this talk. The Hubble Space Telescope deep fields, they revealed the morphology of galaxies back to about 500 million years after the Big Bang. And for reference, the universe is 13.8 billion years. It could be 500, it could be 400, depending on your favorite model of the universe. But that's roughly the furthest back that we can actually see the earliest galaxies. We haven't actually seen, the first galaxies per se. We're still on the doorstep of doing that, but we're certainly very close to the early history of the Big Bang and when the universe first started. And these images, these deep fields, they show that large galaxies like the Milky Way and Andromeda, they formed through the process of many smaller galaxies colliding with each other, sticking together, and forming these larger, more grand design galaxies like the Milky Way and Andromeda. And today, we see those galaxies, the Milky Way and Andromeda, surrounded by many, in some cases, dozens of dwarf galaxies, which we think are the remnants, the byproduct, what's left over from the process that formed the larger, more massive galaxies. Now, this is one way to approach the problem of galaxy formation, is to look at galaxies very far away, back in time. Another way, and that's called cosmology. And another way to look at the problem, another way to attack the problem is through what's called near field cosmology, which just means looking at the properties of these dwarf galaxies, the ones that are near the Milky Way, the ones that are near Andromeda, and asking the question, do they resemble, are their properties similar or the same as their host galaxies, the ones that they combine together to form? And that's another area of study that I'm not going to talk about, but I can certainly answer a question about, but also that is ripe for work with Hubble Space Telescope and with James Webb in terms of making substantial progress in whether those remaining dwarf galaxies are consistent with the properties of their larger parent galaxies. And I think that is my last slide. So I'd be happy to take any questions at this point, Karen.
Great, thanks so much, Ata. And if you enjoyed this presentation, I would like to point out that Ata is also the host of a podcast, Ask a Scientist, that can be found on the FAU College of Science website. So check that out. You'll see all kinds of different topics discussed there. Also, as a reminder, if you have a question, please open the Q&A button in the bottom of your screen, and you can type your question there. We're going to go through those, and we're trying to go through as many as possible during our time here. If we do not get to your question, we will ask our speaker to answer those offline, and we'll post them together with a recording on our website. Ata, as our telescopes are getting better all the time, do you think we can get close to actually observing what happened to the Big Bang during the Big Bang?
So one of my slides, and I'm not going to worry about showing it, I'm just going to point out that one of my slides shows that the further you want to go, closer to the Big Bang, the harder it gets. In other words, exponentially more difficult. So James Webb will take us back maybe another 100 million years, maybe another 150 million years, and that's a 6.5 meter telescope. But to go back then another 100, you'll need at least a telescope that's 5 or 10 times bigger, or 5 or 10 times more capable. So that's where the difficulty is. Can we, or are we as a as a civilization really interested in building and investing that much money, in a telescope or a facility that will push the limits of our understanding of galaxy formation back another 100 million years or 150 million years or whatever? That's really a policy question for the NSF or NASA or the various funding agencies. That's really the question. It's possible. It's just going to take a lot more glass, a lot bigger telescope to get that far back.
Very interesting. Maybe an easier question is whether FAU has an observatory and a high power telescope.
We have an observatory. Yes, it's located on the 4th floor of the science building. Has a telescope in it. It's not high powered, but it is good for amateur viewing of the night sky. And in more normal times, we would have open nights for the public to come use the telescope and look at objects in the sky. Unfortunately, we're not there yet at the moment because of COVID, but I hope that we'll go back to that paradigm in the spring. We'll have to see how the whole coronavirus situation plays out. But we had 2 open nights a month. The first Friday and 3rd Tuesday of the month, the telescope was open for the public, and we have people there to point it at various things and show you different things. But anyway, if we get back on track, we'll definitely make sure to advertise those.
Great, thank you. What is the most distant object photographed?
The most distant object. Well, I'm not fully versed on the highest number, the highest redshift value, object ever observed. But if you remember the Z value that I showed you, I defined Z. Astronomers are always looking for the record highest Z object, and and I think we're up to Z of 8 at the moment. So that would mean that the lines, the spectral lines, are redshifted 8 times greater than where their wavelength should be. But again, I'm not an expert on the record number of redshift. That would be something you could easily Google and find the highest redshift, object we've observed.
Great. Has Hubble been used to find or predict black holes?
Find or predict black holes? Yes, in certain ways, yes. But we really have, Hubble wasn't necessary really to find black holes. Ground-based observations have done a very good job of finding evidence for black holes in different parts of the galaxy, in different parts of the sky. Hubble, of course, helped. There were some areas, some regions that are very crowded, that have a lot of stars in a very small volume, and so you can't observe them very easily from the ground. So Hubble helped in those areas, yes, but HST really has not been critical for the study of black holes. Let's put it that way.
Okay, great. Are there specific types of galaxies that tend to be further away than their counterparts? In our attendee, our participant mentioned that elliptical galaxies contain mostly older stars. So does their age hint at their distance?
Yeah, so that's a good question. Yeah, there is a proclivity for the most distant galaxies to be elliptical, because they're, well, all right. I take that back. Now that I think about it, as far as I know, no, there really is no strong relationship between the type of galaxy, whether it's spiral or elliptical, and how far back we're seeing it. As it turns out, both ellipticals and spirals are formed through the same process. This process of dwarf galaxies, coming together and sticking and colliding and all that. They're formed in the same way. So no, as far as I know, there really isn't a distance or look back time relationship for the morphology. Now, what there is a relationship between the density, the location of the galaxy in terms of other galaxies being nearby, and the morphology. So it turns out that in denser regions of the universe, there's very few spiral galaxies, there's mostly ellipticals, and in less dense regions, there's sort of an equal number of both. So there is that, but as far as I know, there is no distance or time correlation for the type of galaxy.
Great, thank you. How does the Milky Way compare in size and age to other known galaxies?
The Milky Way is fairly, okay, right. How does it compare? Right. Most galaxies in the universe are called dwarf galaxies. So the Milky Way is, as I said, 100 billion solar masses, 10 to the 11th solar masses. Most galaxies are in the 10 to the 7th to 10 to the 8th solar mass range in terms of just numbers. But as far as the mass is concerned, galaxies like the Milky Way and Andromeda are fairly typical. Then there's also galaxies that are much more massive, what we call the giant galaxies, the ones that are 10 to the 12th, 10 to the 13th times the mass of the sun. So the Milky Way, I would say, in terms of the number of galaxies, is unusual because most galaxies, in terms of number, are dwarfs. But in terms of the mass of the galaxies, it's fairly typical. That's how I would say.
Very interesting. Okay, one of our attendees is asking if you wanted to comment on the Belgian priest and astronomer George Lemaitre, who I believe first discussed the expansion of the universe.
Do I want to comment on it? I'm not really a student of the history of astronomy that much. I think I'll just leave that be.
Okay, and maybe we can get to that later.
Yeah.
Will the imaging capabilities of the JWST also aid in checking the current value of Hubble's constant?
Yes, they will. At the moment, well, when HST was launched, there was great optimism that we would be able to measure H0, the Hubble constant, to high precision, better than, say, 5%, which in astronomy, that's like unheard of, We're almost there, actually, with HST. And now we're looking to push the precision of the Hubble constant down below 5%, down to 2%, that range of precision. So yes, we are still working and endeavoring to improve the precision of H0 because it's so important, as I showed you, in that it's a critical part of Hubble's Law. So yes, JWST, one of its tasks is going to be to improve the precision of Hubble's constant, but it's not going to, it's important, but it's not going to be one of its most, highest priority tasks. Let's put it that way. JWST is going to be optimized for the infrared part of the spectrum, wavelengths of light where your eye is not sensitive. It's redder, than where your eye is sensitive. And the reason for that is because it's going to be looking at the most distant galaxies, like I said earlier, looking to find the earliest galaxies, and they're going to be the reddest ones. And it's going to be looking for planets, protoplanets, planets forming or in the process of formation. And when planets are forming, they're still embedded in a lot of obscuration, a lot of dust. And so the light that they'll be emitting will be very red, and it'll be in the infrared. And so JWST will, one of its specific missions is to look for protoplanets forming around proto-solar systems.
Very interesting. Is there a theory about why the leftover dwarf galaxies didn't incorporate into the larger organized galaxies like the Milky Way?
Yes, there's a theory. In any process where you're making something out of a raw material, and especially when you're relying on gravity to do most of the work, there's going to be some stuff left over. You're never going. Well, I shouldn't say never. Those galaxies are still being incorporated into the larger galaxies. It's just that it'll take longer, for all of them to be incorporated. The Milky Way formed over a couple, maybe 2 or 3 billion years. And so the vast majority of it is formed, but that doesn't mean that it's completely done. There are still dwarf galaxies orbiting the Milky Way that are being gravitationally, that are interacting gravitationally with the Milky Way. So the process of formation, you could consider it to be done, but it's not completely done because there's still leftover material that can be incorporated into the main body of the galaxy. In some sense, they're remnants, but in another sense, they're not. The process is still going on.
We're always just looking at a point in time, right? One
Right.
of your slides referred to a period or event known as the expansion of dark energy. Can you explain what this refers to?
I didn't see expansion of dark energy in one of my slides. There's dark ages. I remember seeing that. But maybe we'll talk about that offline. When after we're done at 2 o'clock, I'll look at my slides and we can go back to that.
Yeah, and we can certainly address any of these questions also offline.
Right.
We're almost out of time. I would like to finish up with a question from, I believe, a student who's asking, about how students can get more information on careers in astronomy, cosmology, and also get involved in research opportunities in that field.
Right. So we have a professional organization called the American Astronomical Society, AAS, that has a website with all kinds of information about careers in astronomy and how you would go about, pursuing those careers. AAS.org is the website. It's a professional organization. I'm a member, and it's a treasure trove of information for young students and young scientists who want to move on in the field. And of course, if I'm perfectly happy to talk to that student, and I'm happy to consult in person to talk about what a career trajectory might look like in astronomy and astrophysics.
Thank you so much, Ata. It was a pleasure having you. I know we haven't gotten to everybody's questions, so we will ask Dr. Sarajedini offline to answer all the remaining questions, and they will be posted on our Florida Atlantic University Research in Action website, together with a recording of the whole presentation. So look out for that. Next week, we are going to switch gears entirely and talk about how running is good for your brain. So I hope we're going to see you there again. And don't miss out on looking for Ask a Scientist, the podcast that Dr. Sarajedini hosts on our College of Science website. With that, we hope you enjoy the rest of your day. Bye-bye.